Recording. All right, so we're talking about 3.2, number 48, which says we're supposed to suppose that column J of B is a combination of previous columns of B. Show that column J of AB is the same combination of previous columns of AB. And then we're supposed to notice that, so AB can't have new pivots, so the rank has to be smaller at best, or smaller anyway. And then blah, blah, blah. Okay. So let's start with writing out a matrix B. And I'm kind of considering which component of matrix B. Am I looking at columns or rows here?
Columns.
Okay, so I'm going to write B out as saying it's B1, B2, or I'm just making names for columns. And then we're going to go up to column BJ, I suppose. And then I'm not really sure whether there are more columns, so maybe we end with column BN. You guys with me on this? And then what do I know? Well, I know that column BJ is a combination of previous columns. So that means that, oops, that is not where the vector had, and that goes. That means I can rewrite column BJ as like A1, B1 plus A2, B2 up to previous columns and with, what's the very previous column to BJ?
BJ minus
BI.
1.
Good. J minus 1. Okay. So in saying that this is a combination, they mean that not all of the A1 through AJ minus 1 equal to 0. You guys see why they can't all be 0? I suppose if BJ had a 0 column, then I could think about this as a 0, as a combination of previous columns. Maybe I don't need this. I'm not sure I'm going to use this. I'm just going to tag it quick without, I'm not sure that I need this for later. You guys with me on that? Don't be afraid to do stuff like this, right? Like, I don't need to see my way through the whole problem in order to try to solve this. So I'm just writing down stuff I know. Might not even be right. Shit. Happens. Best of us. All right, let's see. And I'm supposed to show that column J of AB is the same combination of previous columns. So I'm supposed to look at this matrix AB, right? Okay, so if I do A to a matrix that looks like this thing, I got lucky and that equal sign kind of overlap. All right, so if I do A to this kind of matrix of B columns, what do I get? I have this sneaking suspicion that this was the sort of missing portion here. So when you do a matrix A to a set of columns, you get a matrix made out of A done to each column. So I know that I can rewrite this as AB1 in the first column and AB2 in the second column. And I guess let's dot our way out here. And ABJ, that's still not where the vector hat goes in that, Joe. And then ABN in the last column. You guys with me on that? How do I know that's true? Like, where'd that come from? I think that came from my initial, like when I was back in the beginning here, when I was defining matrix multiplication. This is one of the ways I defined matrix multiplication. So we had the kind of row picture of matrix multiplication where we like pick things up and drop them on, right? And then we also had this kind of column picture of matrix multiplication, which was just you do A to each column. So I'm kind of employing that here. Now, I'm supposed to show that column J of AB is the same as the same combination of previous columns. So which column in this picture should I be looking at right now? Like, I should be writing something, something right here. It should be a column. What's the J column of AB?
That'd be ABJ.
Perfect. That's ABJ. Still not where the vector hat goes on that. I don't know why I can't stop that. All right, so that's ABJ. Well, ABJ is A done to BJ. And BJ is this stuff. You guys with me? And then I know that if I'm doing A to a sum with scalars, I can use some matrix rules, right? To say that this is A1, AB1. I don't know where my 1 went from that. It just wasn't there to begin with. Plus A2, AB2. And on. And AJ minus 1, A times BJ minus 1. You guys on board with that? Or did I just use matrix multiplication rules to kind of distribute this thing across? All right, now what?
You're done, right? You just showed that it's also a combination of previous columns.
Oh shit. Yeah, that's a good point, Grayson. I am done. Huh. Cool. Yeah, because these guys are each, so these fellas here, right? This is column 1. This is like AB column 1, right? This thing here is AB column 2. This thing at the end is AB column J minus 1, right? So it is actually the same combination. What they meant by the same combination is it's the same scalars times the same column numbers, right? So like, okay, yeah, check. All right, now what? Well, now the next thing I'm supposed to say is I'm supposed to like notice, I guess, that then AB can't have new pivot columns. So the rank at most went down. Does that make sense? Remember what we're tracking for rank, right, is the number of linearly independent columns. So linearly dependent columns are still linearly dependent, right? Now, there's some weirdness in that linearly independent columns may have become dependent. You guys see that? So I just want a quick thought off to the side here, which is provide A and B with rank of A, B is actually smaller than the rank of B. You guys come up with an example for that? I want two matrices where the rank actually goes down. Let's make them 2 by 2. Just for kicks. Tell you what. Let's take B to be the identity matrix. Right? Linearly independent columns. It's got rank 2. Guys with me on that?
Yeah, A could be a projection matrix or the zero matrix,
Perfect.
something like that.
Yep, either one would work. I'm going to take the zero matrix just to prove that it could be real hard smaller than, right? It doesn't have to just go down by 1. It could go down by pretty much whatever. Okay, no, whatever. But it definitely could go all the way down, right? So then that AB is the zero matrix, which has rank 0. You guys with me on that? Okay, should we take a look at part B here? Oh, whoops. Part B was roughly that. So I'm supposed to find A1 and A2 so that rank of A1B is 1 and rank of A2B is 0 for B is 0, or sorry, is the matrix all filled with 1s. So I think we found that A2 can just be taken to be the 0 matrix. Right?
Yep.
Okay. Any bright ideas for A1 here? What's the rank of B to start with?
Could you do the identity matrix?
Nice. So the rank of B to start with is rank 1, right? It's got 1 linearly independent column. And so if I take A1 to be the identity matrix, then it still has rank 1. Cool. Very nice. Did that get your question, Karen?
Yep. Thank you.
Cool.